my great pleasure to introduce Marco Treves, who has been a regular visitor to UNSW, and we go back a long time. I think we've known each other for 20 years or so. Marco is an expert in many things, but today he will be talking about warm inflation. Please take it away.
All right, thanks for the very kind introduction. So, first of all, I should say that I probably should not consider warm inflation one of the many things that I'm an expert on. I'm not even sure if I'm an expert on many things, but if I am, then warm inflation probably doesn't qualify for them because I have exactly one paper on warm inflation, which is the paper that I'm proof of expertise that I'm going to talk about today. But I have been thinking about this problem for quite some time. So maybe I have something meaningful to say. Let's hope. Okay, so now it works. Excellent. So I don't know how broad the audience is. So I guess it's a little bit broad. At least there's some collider people here and maybe some experimentalists. I'm not sure. So let me try to start very broadly. So I'm a people now call particle cosmologist. So that is, I want to understand the history of the universe based on the fundamental laws of nature that we know. So that is modeling processes that shaped our cosmos on the basis of established laws of nature that we know from particle physics experiment, and vice versa, use the early universe as a laboratory for fundamental physics. So to say, use the extreme conditions that we observe in the early universe as a mean to access physics at energies that are not accessible at present day or any near future laboratory experiment. We all know that we're quite limited by the LHC. We don't even know if the next collider is going to be built. So looking into the sky, we hope to see some signatures of physics at very high energies, in my opinion, is certainly very well motivated. Now, this game can be played at various different levels. So here we see the history of the universe, and these different, I'm sure everybody has seen this picture before. We are sort of looking backwards in time. And well, in this picture, there are the further you go back, the more hypothetical it becomes, right? And this game can be played with CMB, with Big Bang nucleosynthesis, and so on, where it is very relative to the CMB decoupling and at the period of Big Bang nucleosynthesis. We understand the physics very well, so it's not very speculative, even though it's cosmology. It is actually quite precise because this is established physics. But today, I want to try to go back to the very beginning. This very first step shown in this picture, the period of cosmic inflation. And of course, that is in some sense highly speculative, but of course, it makes it very interesting because we are really probing physics at the highest energies, okay? The very early universe. So what is cosmic inflation? Maybe many of you have heard this idea before, but let me try to recap it in one picture. So the idea is to explain the large-scale homogeneity and isotropy of the universe that is observed, let's say, in this CMB picture here. Looks the same in all directions. That's a non-trivial problem because the regions that we see in one direction and the other, they're in principle causally decoupled. They have never been in causal contact if you just extrapolate Friedmann's equation with the known energy content of the universe. So it is a great mystery why in different directions the CMB has the same temperature. And a convenient solution or very popular solution to this problem is that the universe underwent a phase of accelerated expansion in the very first moments of its existence. And this accelerated expansion would solve that problem. The whole observable universe would have been in causal contact at early times. Now, accelerated cosmic expansion is something that we also have today. We see that the universe is accelerating, and we call that dark energy. And the best, I think, well, recently, there have been some doubt about this with very recent data from DESI and so, but still, I would say that a relatively good fit for the data seems to be what people call a cosmological constant, right? There's a slight tension now, but so most people still, or many people at least, still associate dark energy with the cosmological constant. So we have a mechanism in general relativity how we can accelerate the universe with a so-called cosmological constant, but that will not work in the early universe because this inflationary period obviously has to stop at some moment. Otherwise, we would still be accelerating, and we are, well, our universe is not currently inflationary, not inflationary, and in between it wasn't. Okay, so we need some kind of cosmological constant that we can switch off. How do you get a cosmological constant you can switch off? First, physicists follow Occam's razor, take the simplest thing, a real scalar field. What that is, let's see, it might be some effective description or whatever, but let's start with introducing a real scalar field with some effective potential, and then we can draw this picture here with the effective potential, and the field slowly, if the potential is sufficiently flat, there's some early period where the field slowly rolls down this potential, and this period is approximately constant. That is, it practically acts like a cosmological constant because it adds a constant energy density to the universe. The universe is being accelerated. Now, the whole thing is dynamical, so the thing rolls down here. At some point, it starts rolling quickly, so it's not so constant anymore, and then it oscillates around its minimum until it finally settles here. So that switches off the cosmological constant and accelerates the universe. Okay? And also, during these oscillations around the minimum, you can have particle production effects. So this is in this oscillating background, it can produce particles, and that fills the universe with a hot bath of radiation. That's important because in this standard picture, during the first period, here, this inflationary period, the universe is cold and empty because the universe expands very rapidly. So any pre-inflationary form of energy that may have existed is very rapidly diluted. Okay, so at the end of inflation, the universe in this picture is entirely empty, super cool, so to say. And then only during this so-called reheating process, particle production heats up the plasma and then creates what we call the hot Big Bang initial condition for the ongoing history of the universe. What is very important to understand is when you observe the CMB, you observe fluctuations like this, and in this picture, these fluctuations originate from quantum fluctuations and were created during this early phase here. So basically, during this early phase, when the universe accelerates very, very rapidly, quantum fluctuations get sort of, quote unquote, blown up to macroscopic scales and stay there to form seeds of galaxy formation. So but in this picture, there are really clear, distinct periods. An early period where the universe accelerates exponentially, is cold and empty, and fluctuations are created from cosmic perturbations that later form the seed for galaxy formation, are created from quantum fluctuations. And then a subsequent period where the field oscillates around its minimum. In this period, there's a hot plasma being generated, and that then sets the stage for the hot universe. So this inflation and reheating are two separate processes. In some very rough approximation, this, well, maybe not so, but usually this can be described by this equation of motion up here, where phi is this field and h is Hubble expansion. E is the effective potential in which the field moves, and this gamma here is some dissipation coefficient that tells us the efficiency of the transfer of energy from this phi field to everything else, essentially. And the general assumption is that this dissipation coefficient plays no significant role in the early period, and thus, but it's very crucial here because it produces particles. Now, this particle production cannot always be described by a simple equation like this because there can be non-perturbative effect, feedback effects, and so on. But it's zeroth approximation, you might imagine that this equation holds. Okay, very good. This is the standard picture of inflation, and I'm sorry if I bored those of you who have heard this 100 times already. But I'd like to recap it to put it in contrast to what I'm going to talk about today, warm inflation, which is a sort of alternative incarnation of the standard inflationary paradigm. Okay. Before coming to warm inflation, let me talk a bit about the power of inflation and its criticism. One of the great things about inflation is, apart from predicting homogeneity and isotropy of explaining the homogeneity and isotropy of the universe, it can also predict, for a given potential, the spectrum of perturbations that you expect. And we compare that to CMB observations, and it seems that it fits well for some models. However, there are a few questions. So this is seen here. So this is the current observation, you often characterized by the so-called spectral index of the perturbations and the scalar to tensor ratio. So one is basically, this is basically the tilt in the spectrum of scalar perturbation, and this is basically the ratio between the amplitude of scalar and tensor perturbation. Okay. Now, there's been a bunch of criticisms about the standard inflationary paradigm, which I summed up here. And of course, as I wrote there, this list is entirely subjective and arbitrary and subjective. So one criticism has been the initial conditions. So in spite of this inflationary dynamics being an attractor solution, people have argued how likely is it that the initial conditions that initially trigger the inflationary dynamics are actually realized in the universe. I personally don't think that it's a big problem because all these arguments against this, they always rely on some kind of prior concerning the wave function of the universe that we have no idea about. So making any statement about how likely or not likely that is relies on, but to me, it's a very long shot to know anything about this. Okay, so some people consider this a serious problem. They think about Boltzmann rings and whatever. I will not talk about this. The second problem is the flatness of the potential. This only works if the potential here is very flat. Well, it turns out you can easily construct models that have flat potentials. There's no lack of models nowadays. Another problem that people have pointed out is the fact that you need trans-Planckian field values. So the value of the field phi is larger than the Planck mass in many of the popular models. So at first sight, this is not a problem because the field value itself does not represent a physical observable such as energy density. So it doesn't mean that the universe becomes a black hole. However, in the view from a quantum field theory viewpoint, this is a problem potentially, because if you believe, usually QFT is thought of as an effective field theory, and you would generate operators, like you would rate, via gravitational interactions, you would generally expect to generate operators as they go like phi over m Planck. Okay, you would expect all these operators to be present at the radiative level in your quantum field theory, and if phi is larger than m Planck, they're not suppressed, so therefore there's a computational problem. Well, at the classical level, there's no problem here, but if you think about QFT and you think about radiatively generated operators, then you would expect them to scale as phi over m Planck, and therefore there should be gravitational correction to all these potentials.
Does it mean that it requires a spatial scale smaller than the Planck scale, right?
No, it's just, it doesn't, yeah, exactly. So in classical physics, there's no problem. And at first sight, there's no, because basically all it means is that so this is the potential as a function of the field value. And you say this field, of course, the scales here are sort of arbitrary in some sense, but it means that the distance in field space that this field has to pass during the evolution, if you want inflation to last long enough to explain the observed data, the distance, because phi has mass dimension 1, right? So the distance in field space that it travels during the field excursion has to exceed the Planck mass.
But that's not a generic requirement for inflation.
Not a generic, but in many models.
In large field models, yes, but there are plenty of small field models where that's not the case.
Yes.
The reason why people like large field models was that they predict a large tensor to scalar ratio. And this is something that would have been detected by now, but hasn't been.
That's the reason why this is orange and not red in this list. So in many of the simple models, like polynomial models or so, you have these trans-Planckian excursions, and it is not a direct problem because there's no energy scale. It's not probing any, as you say, distances shorter than the Planck scale. There's no energy density. It's not like a black hole. But this, in the QFT, from the viewpoint of doing expansions of the potential, it can be considered a problem. But yes, Jan says there's models that solve this. But I'm going to talk about, now I've talked a lot about things that I will not talk about today. So the things that I will address today are the last two. First of all, there's an uncertainty due to the reheating epoch, because why? Very simple. Fluctuations get generated here. We observe them now. In between, this reheating epoch happened. This reheating epoch depends on not only the shape of the potential, which we know in a given model, but also on the efficiency of this transfer, especially the duration of the reheating epoch depends on how large this damping coefficient is. And we don't know that, so that puts some fork of uncertainty on all model predictions, because you can only translate fluctuations generated here into observed CMB perturbations once you specify how reheating worked. And this final problem, I'll get back to that. The final problem is that the simplest models don't work. Of course, there are not so simple models that work, but since we only have a limited number of observables, this is a problem for the predictivity. So if like the first models that people tried were just m squared phi squared or lambda phi to the 4 potentials, they just have one free, well, actually, no, Starobinski was most of the time. But early models included those where there's just one parameter. And if there's only one parameter, you can measure this parameter in CMB. If I start constructing models with many parameters, of course, it becomes difficult to distinguish them, and you can basically fit anything in the CMB, okay? Just because your model has more parameters than there are observables eventually. Therefore, it is a bit of a problem that simple models don't work, and you can see that here, these are the predictions for sort of monomial potentials, and m squared, phi squared, or lambda phi to the 4 are not even shown anymore because they're so far away from observational data. Okay, so this is a problem in the sense of maybe nature is like that, but it is a problem in the sense of predictability, because if my model needs many parameters, then I can't make predictions. That's the last. Now let's come to the reheating thing. Why is the reheating phase a problem? Because, okay, this is a schematic picture how things work. This is assume this big box here is some fundamental theory of nature. And then in this fundamental theory of nature, I have three different sectors. So this black ellipse up here is the model of inflation, which let's say can be characterized by a certain set of parameters VI. Let's say we Taylor expand the inflaton potential or whatever. There are a certain number of parameters here. And then down here, we have the radiation path that might consist of the standard model and potentially some supersymmetric or whatever BSM particles. There's a set of parameters, very large set of free parameters inside this box, like all the standard model parameters plus all the parameters in the BSM theory. And then the reheating needs to somehow couple the inflaton. The inflaton needs to somehow couple to this in order to transfer energy from here to here. Now, the reheating process in general does not only depend on the small set of couplings that the inflaton has, but also through feedback effects of the produced particles onto the ongoing production, potentially on this large set of parameters down here. Now, the ones in the standard model we know, but all the BSM ones we don't know. So therefore, the connection between CMB observables and the model of inflation a priori depends on a large number of unknown parameters related to these unknown mediators. In a world in which the inflaton directly couples to the standard model, we might not have this problem, because then it's just maybe a single coupling and we can measure it. But in a world where the inflaton couples to our known particles through a series of intermediate mediators, we have a large number of microphysical parameters in the game, which means that it's very difficult to model this process. Let's put some uncertainty on the, I mean, this is not so much of a problem if you just want to understand CMB data, but if you want to interpret CMB data in the frame of particle physics theory, then this is a problem. Okay? Now, warm inflation. Alternative viewpoint. Can warm inflation solve this? What is warm inflation? It's an alternative viewpoint in which this period of inflation and reheating are not separate. We basically say this dissipation coefficient here is relevant at all times. And during inflation, the universe is not cold, because there is a kind of steady state situation in which particle production, through dissipated effect here, exactly compensates the dilution of the radiation density of the plasma's density due to Hubble expansion. Okay? That needs a relatively large dissipation coefficient, because Hubble expansion is very good at diluting, especially during exponential growth. Hubble expansion is very efficient at diluting energy densities. But you could imagine.
Can I ask a question here? Sorry, Marco.
Yes, of course.
Yeah. So, but this is model dependent, right? How much how much it's going to feedback is going to heat it? Like how much heat you get? I mean, if it's like really weakly coupled or something, you may not get adequate feedback, right?
Well, of course. That's the challenge. That's the challenge, to construct a model. Okay, what people have done in the early days of this, they have just written down some coefficients, say, okay, let's assume this thing has the following scaling. What is the pheno that we get from that? But a big problem is to get actually in a concrete quantum field theory setup, write down an action that actually gives me such a large dissipation coefficient. Okay. You do need this sizable dissipation coefficient. And you can, of course, say, oh, I'm a CMB observationalist. I'm just writing down some effective parameterization and plug in numbers and see this works. That's all fine. But if you want to show that this actually works from a particle physics viewpoint, you need to write down a concrete action that gives you such a large dissipation coefficient without causing problems elsewhere. And the second one. And I will get to that point in a second. Okay. Qualitatively, the picture is basically that there's a steady state solution in which particle production exactly compensates the Hubble expansion, and you have a hot plasma during inflation. That has the impact that the cosmological perturbations now are not just sourced from quantum fluctuations during inflation, but due to the presence of the thermal plasma, there are also thermal fluctuations that contribute to introducing perturbations in the CME.
Can you explain what compensates what in this equation?
Yes, I'll try it with these equations here. Okay. So here, this is so basically in zero approximation, in very simplified approximation, there's a set of two equations. So one of them, oops, why does this not mark it? But here, one of them is this equation here, which is the equation of motion for the scalar field, which again has Hubble expansion, dissipation, and the effective potential. The other one is for the radiation density R. Okay, so radiation density is just density of all particles in the plasma. So the point is that this radiation density, it gets diluted through this Hubble dilution term here, but it receives energy from the dissipation, because this dissipation here, of course, total energy is conserved. So the energy that is taken out of the inflaton field is dumped into radiation. And that leads to a source term on the right-hand side of the equation for the radiation density. Okay, and now you can find at which temperature this stabilizes by just demanding that rho dot R is 0, and you find that there is a state. Well, there is, in principle, you can write down this stationary solution, where this is just a radiation density formula. And well, you can find the stationary temperature for given gamma and given V prime prime. Okay.
So you assume local equilibration.
Yes. Okay, yeah, very good point. So in this picture, we assume that the field rolls still very slowly. So on the time scales on which the background field changes, the plasma of produced particles quickly reaches thermal equilibrium. That's of course an assumption, but if the field rolls slowly, it should be, well, doesn't sound crazy to me, you know, because this is a very adiabatic, slow process, the rolling of this field. Huh? Okay. So the challenge now lies in the fact that this is all easily written down. Can I construct a quantum field theory that gives me the effective potential and the dissipation coefficient that actually maintains such an evolution? Okay. And before getting to that point, I'll introduce people usually distinguish two different regimes. So this Q parameter is the relative size of dissipation and Hubble dilution. So in this equation here, there's Hubble dilution and dissipation. The Q parameter tells us what is the ratio between them. So is Hubble expansion more important when it comes to slowing down the inflaton field, or is dissipation more important? Okay, for Q larger than 1, dissipation dominates. For Q smaller than 1, Hubble expansion dominates. What that means is in the so-called strong regime for Q larger than 1, the dissipation here, it dominates the background evolution of the inflaton field, and it is important for sourcing perturbations. In the so-called weak regime, where Q is smaller than 1, then in this equation, the gamma is kind of negligible. So therefore, the evolution of the background field basically works like in standard cold inflation. But still, you see a difference to cold inflation because the presence of the thermal bath still gives you different CMB predictions, because perturbations are being sourced by the presence of the thermal bath. Okay. These are the two regimes. And then from this, you might, if anybody who is familiar with the slow roll parameters in inflation, you see that you can modify these slow roll parameters that are usually used during inflation to characterize how slowly the field grows. There's this Q appearing here that I just defined, and basically if you set Q to 0, you get back to the standard slow roll parameters, and for non-zero Q, you see that it actually makes, at first sight, slow roll easier to have this Q. You know, it means that, which makes sense because the field is not only slowed down by Hubble damping, but also by this dissipation. So therefore, it should be easier, in principle, realize slowly rolling for a certain number of E-folds of inflation. However, so this solves some of the problems. As you will see, this works with a simplified to the 4 model, as I will show later. So that solves the problem that simplest models might not work. It also eliminates the uncertainty due to reheating, because basically there is no separate reheating in the epoch. Basically, inflation directly produces thermal bath and you directly exit into the hot universe. But it causes another problem, namely the flatness of the potential. And this is why. Let us take the equation that we just looked at. So this dissipation coefficient and the effective potential, they are not independent of each other. Because you can write down some tree-level potential, but if you have a thermal bath there, then you create thermal corrections to the potential. So those of you who follow these lectures on thermal QFT that I'm giving this week, they might be familiar with these two diagrams that I used as example diagrams in yesterday's lecture, okay, in scalar field theory. So that's why I'm making this simple example here. So for simplified to the fourth theory, you would get a correction to the potential, and there should be t squared here. Okay, there is a mass squared correction that goes lambda t squared, so I forgot the square here. And the dissipation coefficient goes like this. But anyway, in spite of the missing square, the point that I want to make here is that whenever you want to make, for simple scalar coupling, whenever you want to make the dissipation coefficient gamma large enough to matter, you unavoidably generate a thermal correction to the effective potential. Okay? So you get it, as I said, so this is, you would get dissipation from this kind of diagram, which has an imaginary part, and this creates, switching this on, like it's impossible, at least in simple scalar field theories, to generate a large dissipation coefficient because that requires a large coupling constant, but a large coupling constant automatically leads you to a large thermal correction to the potential. So therefore, naively, it becomes easier to do inflation because of what is written here. So if I make my Q larger, I suppress my slow roll parameter, say, yay, slow roll is much easier now. But unfortunately, as I increase, the only way to increase Q is to increase the coupling constant. And if I increase the coupling constant, I also increase V prime with the derivative of the potential. So therefore, my potential becomes more steep. And if you look at these, because of these thermal corrections to the potential, so therefore you're increasing Q, but you're also increasing V prime, right? And it turns out to be more difficult to realize inflation rather than easier. It's the point that Linde and Yokoyama made long ago. So while the initial claim of Pereira said this simplifies inflation, Linde and Yokoyama said no, generically, this actually makes it more difficult because the effect from the thermal correction to the potential tends to outweigh the effect of enhancement of the dissipation coefficient. Ways around that? There is a way around that called from non-perturbative productions by there's from a non-perturbative effect called scalar heating. So the basic idea is that if I consider a potential with a shift symmetry, then the potential can be corrected from protected from thermal corrections. Okay. So if I consider straight away the following Lagrangian, here there's some potential which I haven't specified. We can for the moment set that to 0. And then if I have this axion-like interaction where G mu nu is a field strength tensor, then this interaction here has a shift symmetry, okay? So this interaction can generate me a dissipation coefficient without introducing a large thermal mass or thermal correction to the effective potential because the shift symmetry protects my potential. Now, if I only have this, then there will be no inflation because the shift symmetry also implies that I never start rolling. So I need to add some small breaking of the shift symmetry in order to get the inflaton field rolling. Yeah? But this can be done, a small breaking might be sufficient. Okay? So this gives the following equation of motion, where if I now take the expectation value, where this is now expectation value, quantum statistical expectation value of things, where the right-hand side is given by this GG dual expectation value thereof. So now it all boils down to calculating this operator here, and this has been first done by these gentlemen here. And they found that in the slow roll regime, there is a non-perturbative effect that comes from so-called Federon damping that gives you a large dissipation coefficient from this. That will give you more inflation. Meanwhile, it has been calculated in various different regimes, this coefficient. Okay, let's not go on with that. Now, how does that work? Here's a sketchy picture. So you couple two GG duals of a non-abelian gauge theory. So non-abelian gauge theory, as you might know, have an infinite set of vacua that are related to each other by so-called large gauge transformations. And these vacua can be associated with topological numbers called Chern-Simons numbers. So this is a very simplistic one-dimensional illustration of this large field space thingy. So basically all these vacua are exactly equivalent, and you don't know which one of them you are. But if the system makes a transition from one to the other, that is a physical effect. And this transition is often sloppily called a scalaron. Well, in principle, the solution in field space is called scalaron, but the transition is also called scalaron. Now, in vacuum, it is very, very unlikely that you tunnel. The only way to get from here to there is to tunnel, and that, well, that might be considered, it might be as generally suppressed. But at finite temperature, you can jump over these barriers, and that means that these kind of transitions happen frequently above a certain temperature in any non-abelian gauge theory. So if it's just a pure Young-Wilks theory, this happens randomly in any direction. But if you couple it to an axion in this manner, then that creates a preferred direction for these transitions, singled out by the sign of the derivative of the axion field. And that means that there is, well, effectively what this does in the end is a net transfer of energy from the axion field to the plasma. Okay, and that is characterized by this here. You get, if you evaluate this, what this gentleman has done, you find that this is related. You get such a term, which basically is exactly the kind of dissipation term you need. It's phi dot times some coefficient. But this coefficient can be evaluated to be, well, it has this behavior here, where alpha is the gauge fine structure constant, and C is the number of colors in your theory, and F is the, well, is this axion decay constant that is related to this interaction here.
Is gamma is a, you know, well, let me call it what is called assisted tunneling rate, or what?
So this gamma here is the will be identified with that gamma here, but this equality here, of course, relates it to the so-called scalaron rate. So this gamma scalaron is, but that's a dimension 4 quantity, which tells us which. So this so-called scalaron rate would be a dimension 4 quantity that tells us like the probability per volume unit of scalar transition.
No, I understand this, but anyway, is this what is called temperature-assisted tunneling rate? What is it? Because, you know, well, in principle, this sort of mechanism is considered in many, many problems, right? That you have a tunneling rate at 0 temperature, and then if you raise temperature, you can either go above the hump, or you can slightly raise the energy and tunnel, still tunneling, but you know, not that deep tunneling. This is my question.
Ah, I see. Okay. To be honest, so this is okay here. I'm not sure which process dominates here. Because both processes can change the Chern-Simons number. Like, you mean you don't tunnel here, but you tunnel like halfway up or something.
For example, right? And so, usually this dominates. Not you don't go to not jumping over.
I think okay. I'm not sure what is the answer in general, but yeah, today I'm going to talk about this with QCD, and the temperatures at which I do this will be 10 to the 13 GeV. So at those temperatures, I think there's absolutely no problem jumping over, and I suspect, okay, to be honest, the value of this rate you took from lattice results from Guy. But I suspect at these very high temperatures, the dominant process is jumping over the barrier because it's 10 to 13 GeV, which is much, much larger than the QCD scale, right?
But what is the height of the hump?
That height of the hump is somehow related to the QCD scale. I don't know the exact value, but it's much, much, much smaller than 10 to the 13.
I mean, you have to, I think you have to specify the decay rate F. I mean, sorry, the overall 1 by F, because that will go into the scalaron, overall scalaron count.
No, but F doesn't, if this hump is a property of the Young-Wilks theory, so it doesn't depend.
Yeah, but, so, I see. So that's what you mean. Okay, by the hump. Okay. Yeah, sure. Yeah. That's the size of the GG dual.
Exactly. So that's, so for the, that is ultimately related to the scale at which this periodic potential is generated.
Then you're saying that temperature is so high that we can safely forget about this.
Yes. So in the particular application that I have, so in general, I'm not sure if this statement is correct, but in the particular application that I have in mind today, the temperature is so high that I'm pretty sure that real jumps will be the mechanism.
But then why we end up in 1 minimum?
Nowadays, okay, in the early universe, we don't end up in 1 minimum. So the whole point is that in the early universe, this rate is very high. So this process happens very efficient in the early universe. But as the universe cools down, nowadays we will end up in 1 minimum. Okay, so in the early universe, Chern-Simons number changing processes are unsuppressed. So they unsuppressed means they can happen considerably faster than the Hubble rate. But as the universe cools down, we eventually settle in one of these minima. Does that make sense?
Why do we, if you go through the stage where temperature is so high, this is exactly my question, why we end up in a minimum?
Because the universe cools down due to Hubble expansion. So initially the temperature is very high, so Chern-Simons number violating processes happen very frequently. But as the universe cools down, the thermal energies get Hubble diluted, and eventually you settle in one of those minima.
No, some part of universe will be in one minimum, another part in another minimum.
That's possible.
That is possible,
That's
yes,
possible.
that's possible. So there are different ways of what can happen. So that
Do you end
depends.
up with topological defects then?
I don't think so, because in QCD, otherwise you would have topological defects anyway in QCD, right? This I will do it just with QCD. So then,
You could.
I mean,
Yeah,
this
QCD
goes
axioms
into the
require
direction of.
topological defects.
So I have not thought about this because for the standard QCD axion, there are different regimes, right? That this misalignment can be. There are different regimes in which it can happen. Like it depends on different scales,
But I
right?
guess you are making this happen during inflation anyway, so you're probably safe, right? You're probably just in one vacuum and it's expanded away. So we just in one place and we wouldn't know about the others. Maybe.
No, I mean, you only settle in one vacuum once the temperature has dropped low enough, which in your scenario happens after inflation.
After
ended,
inflation?
right?
But yes, okay.
Yeah, that's the thing. It's during inflation or after inflation, very important. And you probably will have topological defects.
The inflation ends at temperatures that are much, much, much above the QCD scale. So,
Yes.
so I would argue that the problem.
So this is QCD.
Yes.
Like not fake QCD, real QCD.
Eventually, well, this stage it can be any numbers theory, but in the end, in my model, it will be QCD. Maybe I should decelerate a bit. Sorry to interrupt, because maybe I was a bit too pedagogical in the beginning. Now the interesting stuff comes. Okay, so anyway, let's assume this all works. Then, in principle, this gives me a large dissipation coefficient that can give us this warm inflation mechanism. But there's a problem that has been pointed out, the problem of light fermions, because you know the standard model and all the interactions that we know, they have light fermions. Now the problem is if the gauge field is coupled to fermion, there's also a coupling to the axial current, which is called this is axial anomaly. So in the presence of light fermions, the evaluation of this operator that I showed here actually gives you this here, right? Because the gauge field is also coupled to the fermions, and you produce, every time you do such a Svedron transition, you can produce axial charges, right? And the problem is the effective coupled set of equations then for the inflaton field and the chemical potentials for the axial charge looks like this. And you see the same term on the right-hand side. That is a problem because there's no stationary solution that gives you efficient dissipation. Because eventually the system will settle at the point where the chemical potential is stationary, meaning mu dot is 0. And then if you want the right-hand side to be 0, that makes this bracket 0, but that will also make that bracket 0. So that means the dissipation term disappears. Okay? So this is known as the suppression of dissipation from the generation of chemical potentials. So the Svedron transitions generate axial chemical potentials in the plasma, and those axial chemical potentials backreact and eventually kill the dissipation term. Okay? Right, so basically, if I want to make the right-hand side of the equation for mu 0, then it means that also the right-hand side of this equation is 0 because they're the same. Good. Now, there are various ways of trying to avoid this. One can either have chirality violating interactions amongst the fermions, for example, a U-cover coupling. It turns out in the standard model, only the top quark has a U-cover coupling that might be large enough to actually do this. We can introduce another SU2 group. Yeah, I will run a bit over this to get, as I realized I'm taking over than I wanted. So basically, could be U-cover coupling. One can go through various considerations, but basically in the standard model, most of the U-cover couplings are too small to lead to a significant correlation of chirality to avoid the suppression of sphellaron heating from fermions. One could introduce another sphellaron, so I could just say, well, I just introduce another Young-Mills theory that I couple to the fermions, but that doesn't couple to the axion. And then basically the fact that then this other, well, that would create an additional term on the right-hand side of the second equation, but not on the right-hand side of the first, and that would avoid the conclusion that whenever this is zero, then also that is zero, right? I could imagine spectators, so even if my fermions themselves don't have any chirality violating interactions, maybe they connect to a sector that does, and I can transfer chirality one from sector to another. Possible, but it requires, again, introducing an extended sector. So I need to introduce more ingredients, right? So here I need to introduce another SUN gauge group. Here I need to introduce some extended sector to which I couple. But there's a final solution, which is Hubble dilution. You notice there's also this term here, right? A Hubble term. So the conclusion that the stationary solution where mu dot is zero can corresponds to this bracket being zero is only correct if you neglect Hubble expansion, right? Because Hubble expansion also dilutes the chemical potentials. And quite surprisingly, before we wrote our paper, people never thought about that. And then, well, we've outlined all these different ways how one can solve this problem, but it turns out that Hubble expansion alone is enough to avoid the problem. For several years, people have claimed that warm inflation with standard model interaction doesn't work because the standard model light fermions would spoil the dissipation in the way that I just outlined. But it was entirely forgotten that the chemical potential also is subject to Hubble dilution. So it turns out if you consistently solve this whole set of equations, including this term here in red, then it turns out that QCD can actually support warm inflation. Okay. That's that. So previously people had pointed out that Young-Mills theories can do this, but they always introduced an extra dark Young-Mills theory because they said, oh, with the standard model it doesn't work because the fermion chemical potentials kill this sphellaron damping, and therefore I have to introduce a dark Young-Mills theory, another gauge group SUN that has no other purpose than giving warm inflation and never again shows up in the history of the universe afterwards, which I found very unsatisfying because introducing no entire new gauge sector without just single purpose use, I didn't like that. What I liked about this scenario that I'm trying to sell to you today is that here we can do it with a known standard model interaction, QCD, on chromodynamics. That makes it very minimal in the model. Basically, if I include the Hubble expansion into the game, then I can introduce an effective, well, by finding the stationary solution, I can find an effective dissipation coefficient and rewrite these equations here with some. Well, now I don't have the chemical potentials anymore. I only have the coupled equations of the inflaton field and the radiation density. And I've absorbed the effect of the chemical potentials into this effective dissipation coefficient. Now you see this dissipation coefficient depends on the previously defined sphellaron rate, on age, and on various things like the number of fermions, the number of colors, temperature, the axion decay constant. Conceptually, we are done now. Now it becomes a question of plugging in numbers and see how things work. Okay. And of course, this is a generic setup. I haven't specified V yet. Phenomenological, so there are two things. First of all, I have to plug in numbers and see if I can actually make it consistent with observation. And second of all, I have to specify V. What we specified is a very, very minimal model. What can you do? Lambda phi to the 4, the simplest model that anyone can think of, right? Single parameter, dimension is parameter, yeah. Just extension of lambda phi to the 4 to the standard model. It avoids this complicated picture that I showed, basically complication in this picture where there are all these mediator fields that we don't know, there's many assumptions. This scenario is very simple because the whole theory is, apart from the standard model, only has two parameters, the axion decay constant and the lambda coupling in the potential. It's an extremely minimal extension of the standard model, just an axion-like particle that couples to QCD with an axion-like coupling with a lambda phi to the 4 potential that slightly breaks the shift symmetry. Okay, now there are two free parameters, but after matching the amplitude of CMB perturbations, there really is only one free parameter in this model. Because we have already observed the scalar perturbations and the amplitude is well known, so matching that observational data fixes a combination of this f parameter and the lambda parameter. So it's a single parameter model essentially. Okay. Good. We checked that the transition to radiation domination seems to be fast. Unfortunately, we cannot simultaneously solve the strong CP problem because this coupling could, in principle, also solve strong CP problem. Unfortunately, with this choice of potential, we cannot simultaneously. There's no value of lambda that we can pick that simultaneously gives us warm inflation and still solves the strong CP. It would be interesting to see if that changes if I change to different potentials, right? But at least for the simplified to the 4 potential. Unfortunately, I can't solve the strong CP problem, but I can do warm inflation. Good. Now, so far I've only been talking about the background evolution. Now one can make predictions for the CMB. And these are our predictions for the CMB. Oops, sorry. The spectral index and scalar to tensor ratio. Now, we didn't derive the formalism to make these predictions from first principles. We just took formula from the literature. Now, I am aware that the theoretical uncertainties in the prediction for warm inflation are much bigger than for cold inflation, standard inflation, because the derivation of the formula that gives you the CMB predictions has been less rigid. Let's put it like that. For cold inflation, it has been quite rigorously derived long ago. For warm inflation, there are several approaches in the literature how to compute the CMB. We took, I would say, most recent 3 formalisms that there are. We found that for our model, the discrepancies between what they yield is smaller than the current 2 sigma error bar of the observation. So therefore, we acknowledge that there is an uncertainty, and then we just pick one of them. We acknowledge that there's a theory uncertainty in making CMB predictions, but by comparing 3 different formalisms in the literature how to make this correction, we concluded that the differences are comparable to the 2 sigma error bar on NS. So therefore, I think even though the precise, this is basically, I said, these are the predictions for different values of lambda. Basically, you can draw a line through them. When I said it's a single parameter model, you can see that because it's a one-dimensional manifold in this, I mean, it's a single line in this plane. And here you see for various values of lambda, the corresponding predictions for R, for NS, for this Q parameter. And for the temperature, you see here it's around the stationary temperature is around 10 to the 12, 10 to the 13, something GeV. It's very large values of the temperature. So yeah, as I said, take these CMB predictions with some grain of salt, but the fact that they are not the final answer, but as I said, the uncertainty by comparing the different formalisms, they're all 3 formalisms that we use reveal that our model predictions lie within the current observation data, but if they go a little bit left and right, depending on which formalism you use. Okay, that's to be clarified. Now, yeah, that's that. Now, for current observation, doesn't matter. For future observations, it will matter. So I'm a bit pessimistic now. I always used to show these pictures about the amazing perspectives to observe the CMB. As many of you know, one of these pictures, namely the CMB-S4 here, has recently been hit by US government cuts. And the Japanese Lightbird satellite is also not so obvious, I think, how well funded it will be. I don't know. I've heard some rumors. However, there are some other alternatives, well, existing facilities in Chile, of course, like the Siemens Array. And so there's an upcoming thing in China, the Ali Observatory here. And well, also non-CMB observations can tell us something about NS and R, such as Euclid and SKA. So why I'm showing you all of these, because the posteriors that I'm going to show you, what we can learn about lambda with future observations, I have aligned what could be done with CMB-S4 if it happens, which at the moment seems very unlikely, but just to show what a facility of this kind could do, I think it's still instructive to have a dotted line there. Here we see what could we learn about, as I said, it's a single parameter model essentially. What can we learn about this parameter with observations from certain probes? So we see that the current Planck and Keck, Keck data, this is lambda, this is the posterior, basically doesn't really restrict lambda very much. It's this blue posterior. But you can already see here the entire line lies within the Planck data, right? So basically Planck doesn't tell you much because it's all in there. Now, CMBS4 or something like CMBS4 would give you a very narrow posterior that is so narrow that you can't even see the top. But even if CMBS4 doesn't happen, we work together with this RDCPT collaboration, even with the Chinese observatory, we could still get a decent measurement of lambda in the future. All right, I think I'm approaching the end of the time, so I'm not going to read out everything that is written here, but instead just try to sum up. So we have investigated an alternative to the standard inflationary paradigm called warm inflation. This the idea has been around for a very long time, but there have been serious challenges in realizing this in concrete QFT incarnations. And the most credible incarnations that we have seen before we wrote our paper all involve extensions of the standard model by dark SUN gauge groups that have no other purpose than driving inflation. So what is new in our paper is for the first time realizing that this can actually be done with QCD. And the reason why previously people thought it cannot be done with the QCD is because the light fermions, but we showed that this fermion, the Hubble dilution of the chemical potential, is sufficient to overcome this problem of light fermions. And we also showed that when choosing a very, very minimal lambda 5^4 potential, we can fit the CMB and have a very predictive model that can be tested with future observations. And the nice thing is, in principle, one can search for this axion, of course, also in the laboratory, so you can see the signature in the CMB. If we are lucky, we can also find it in the laboratory, and then we have really probed inflation and the connection between particle physics and inflation through a combination of laboratory experiment and cosmological observations. So I don't want to go beyond time, so I will stop here and rather listen to your questions and talk more. Thanks a lot for your attention.
Thank you, Marco. Do we have any questions online? Just speak up. Well, you can think about it some more. Do we have any questions in the room?
Yes.
So you say that your lambda which you require is not consistent with lambda which is you need for strong CP or for dark matter. Can you quantify the statement?
So,
how inconsistent? 10%, 100 orders of magnitude?
well, let's put it like that. When you want to solve the strong CP problem, lambda would have to be lambda. So this lambda here is already very, very small. Okay? In order to solve
this lambda, it's your lambda.
This is my lambda that we need to fit the CMB. And you see it's something like -21 or so. It's ridiculously small.
I forgot, it's in 4D, it's dimensionless. Right?
Yes, dimensionless, exactly. It's a dimensionless quantity. That's a ridiculously small number. The problem is that even this ridiculously small number breaks the shift symmetry so much that it doesn't solve the strong CP problem anymore. So if you set lambda to 0, then our theory basically becomes the QCD axion. Okay, effectively. Then it solves the strong CP problem. Of course, you need some UV completion, but okay. But even these very small lambdas here are enough to kill that. Okay, and in this model, basically, we estimated how much dark matter, okay, this QCD axion can simultaneously solve the strong CP problem and be dark matter, where the dark matter basically, if you go to low energies, you have this periodic potential for the axion that is generated, and then it oscillates in there, and that gives you dark matter. The problem is that in our theory, the presence of this lambda pushes you so close to the global minimum because it rolls towards the global minimum that the amplitude of these oscillations is so small that the contribution to dark matter is, I forgot. It's a small fraction of the observed density. I don't remember the number, it's very small. So quantify, yeah, you see, quantify means even these very, very small lambdas are too much to be consistent with the dark matter interpretation. And the reason for that being is that even these very small lambdas are large enough to sort of push your field. Yeah, you will end up too close to the minimum in the end.
And I forgot, which lambda do you need to explain this cusp in galaxies?
It's a different problem.
cusp in galaxies.
Well, it's related because it's
You need to be
quantum
the dark
pressure.
matter. Yeah, but you need it to be the dark matter for it to matter for the cusp.
Yeah, here you got, because
This
here
is not even dark matter.
here it contributes to
I
dark
understand,
matter,
but
but
that
it's
is that
subdominant.
is the simplest. Of course, it's probably mass.
You mean like self-interacting dark matter? If you say I have like
Yeah.
axion-like dark matter with some self-interaction, that then
Self-interaction, right?
yes, I don't know. I've not worked on that. I don't know what value you need. Would be interesting, but the problem is here. So maybe this is an interesting question. So maybe this stuff would give you solve the cusp core problem if it were present in a sufficient amount, but it's not. So therefore, at least for this potential, like the total abundance, well, the total amplitude of these oscillations is too small to make up a sizable fraction of the dark matter, and therefore it will not affect galaxy formation in a significant way, even if it has the self-interaction. Of course, it's the ultimate goal to come up with this is the kind of the framework. This framework you can think of with different potentials. So to come up with a nice potential that can ideally do everything at the same time, dark matter and strong CP, and that would be awesome, but okay, it doesn't work for lambda 5 to the 4. But okay, I think it's already quite cool that lambda 5 to the 4 gives you warm inflation with standard model gauge interaction. And solve one problem at a time, Yes,
Yeah, I had one. Oh, actually, I had a few, but I'll ask one maybe.
Yes. We can alternate one you, then one you.
Yeah.
So I was going to comment on the value of lambda. So 10 to the minus. So first of all, I was going to comment on the value of lambda. I mean, that's okay. I don't know what unnatural means anymore, but that small number uh, it seems to be a bit unnatural. Like you're specifically tuning numbers to that value in a very peculiar way. That was one comment I was going to make.
I
Sure,
would
it
argue
works, it
that
works. I mean, if nature gives you that value, yes. I mean, I don't care if it's natural or unnatural in a traditional sense, but
I would argue that naturalness, okay, in my opinion, there are two ways to look at naturalness. One of them is, does something have the value that I like? That is just a personal opinion. Then there is a more well-defined concept of naturalness, which is the technical naturalness.
yeah. So the question is this technically
Yes,
natural?
there is a symmetry in the limit where lambda goes to 0. So you have the shift symmetry, right? Okay, there's some symmetry, this shift symmetry that is restored. So you could argue that way. But to be honest, this is not my motivation. My motivation is
I agree. But so my my really question is, so what kind of potential can you would you sort of think of when you say that, okay, apart from lambda 5/4, like if you took something like more general Coleman-Weinberg potential, would that work?
we tried m squared phi squared and lambda 5 to the 4. M squared phi squared gives you the wrong CMB. Lambda 4 gives you the right CMB. So we picked lambda 5 to the 4.
What's particularly wrong about the CMB?
It doesn't fit. I forgot. Kim did that part.
So I'm just generically asking what are the features of the potential that you might want to look at? Like in the sense that if you wanted to construct a potential, just writing down something as a polynomial series and
See, I'm not a model builder.
okay.
So my creativity ends at lambda 5 to the 4,
Fair enough.
But, because there's always top down and bottom up, and there are some super crazy potentials in the Encyclopedia Inflationaris that are
Yes.
like
I have seen that there are absolutely insane potentials, which I don't even know how to generate those potentials.
If you go to Christophe Rochefort, he would tell you, oh, there's this string model in which this potential is absolutely natural, and I'm like, okay, fine, I don't know, I'm a bottom-up
So
guy.
I have seen people claiming, for example, I don't know, because a certain class of what are called holographic models generating warm inflation, but yeah.
So you might, for example, if you look at, I don't know, this Starobinsky model, it's minimal in some sense, but the potential, is that natural? I don't know. Maybe it is, So to me, I would say I would pass that question back to the model building community, because to me, as a bottom-up phenomenologist, I just start with polynomial potentials. It works fine. If some model builder tells me, okay, this is what we should get, I'm happy to plug it into the equation, but I'm not really a model builder myself, so I have no idea what is natural or not.
Okay, Fair enough.
I was driven here by minimality because one of the things that really bothered me here when I made my ranking of the problems of inflation is simple potentials don't work. This is not something about the shape or so. It's simply an argument about the number of parameters. Like we only have this and that many observables. So potentials that have 10 free parameters, no matter how beautiful they are, they're phenomenologically not so interesting because I can't actually constrain those 10 parameters with any near future observation, right? Models with only one parameter, like Higgs inflation or Starobinsky or whatever, simple things are easy because they have few parameters that they're testable, you know?
Yeah.
Yeah, you wanted to ask.
Can you go back to that table with the benchmark values?
Yes.
Yeah, good, perfect. So T is the reheating temperature, right?
Yes, so T here is the stationary temperature. And since we estimated, even though we didn't fully simulate it, but estimated that the transition to radiation domination is very quick, it's also roughly the reheating temperature.
Okay, so T is larger than F, right?
Yes, so there is...
So you're basically probing a regime. So at least if you think about when you generate some axion-like potential from some normal scale, complex scalar field, you're basically probing a scale which is beyond the symmetry breaking scale.
So here, this is you're referring to this point here, right? You're saying this is a non-renormalizable interaction, so to say?
No, I was just comparing the decay constant, the third column with the fourth one.
Yes, so... Okay. So the way how I see things is that this thing here is a non-renormalizable interaction. And it's therefore I interpret it as an effective field theory. And I can write down what is the maximal energy at which this effective field theory is valid. That is not F, but there's also this factor A pi and some stuff like that. So we see we are within the range of validity of the effective field theory. However, if you write down specific UV completions, it could, of course, be that your effective description breaks down before this lambda cutoff. So
yeah, that's what I was basically wondering. There could be effects from that.
Exactly.
UV
So,
physics.
very good point. So this is a QFT description, and it is a self-consistent QFT description in the sense that this effective field theory, our temperature always below, but remains below what we call lambda cutoff. But lambda cutoff is, of course, the point where we know for sure that this description breaks down. Okay, and we're safe in that regard. But if you look at concrete realizations, in particular, if you look at the standard ways to implement the Paget-Quinn things, if this were the Paget-Quinn axion, I think we would have a problem. Because we would see effects from the
real scalar.
But this cannot be the Paget-Quinn thing anyway, because we have the lambda phi to the 4th. So
you have to.
It has to be something else anyway. And then I would say we are safe in the sense that this here, we check that for all these values, we are at least an order of magnitude away from the EFT cutoff of the effective field theory. But as you point out, in specific realizations, the cutoff can be lower than what we call the cutoff here. And then you might have to do a model-specific thing to see if it still works.
Yeah, I think I was thinking maybe you can probably do clockwork on this to suppress certain. Okay, anyway.
Yeah, good point. Nice catch.
you can do clockwork on it, yeah.
You can look what?
You can do clockwork on this to suppress some
clockwork. Clockwork. Yeah, maybe. I've never been convinced by this clockwork stuff. But...
No one is. That's not the point, I think.
It looks very fragile and weird and constructed to me, but don't tell the people who made it that I said that.
So do I interpret the second column correctly in that your model still has the Transplanckian issue?
Yeah, it still has the Transplanckian issue. Absolutely. So it's, well, the way how Sebastian phrased it is we slightly improve on the Transplanckian issue, but we don't solve it. No. But of course, this is not so surprising because after all, lambda phi to the 4 is a large field. Well, yes. Initially, we hoped that the dissipation coefficient could be large enough to reduce the required field excursion below the Planck mass. But at least for lambda phi to the 4 doesn't work. Again, if you play around with different potentials, it might work. But to me, the main part of this work is the proof of principle to two things to me are the main point here. The first one is proof of principle that it can work with QCD. And the second is a minimal potential fits the data, right? Because here there are two things. One of them is this coupling here that gives you the dissipation coefficient. And there the main message of the paper is this can be done with QCD. You don't need any big extensions of the standard model. It can be done with known gauge interaction, period. And that is the main message of the paper, in my opinion. Then, of course, another thing is, and on top of that, with a very simple potential, very, very minimal potential, very testable, we even managed to fit the CMP data. But of course, this is meant to open a road towards a new, an avenue towards a new possibilities of model building where you can find some potential. We or somebody else can find potentials that might work better. Maybe there are potentials that can solve the QCD problem at the same time. Maybe there are potentials that can solve the transparent gain problem. For me, this paper is just a short letter. It's just a proof of principle. You know? Yes.
Can you lower the temperature where it all happens? Because it's all at...
Not with this potential. Again,
for that one.
again, you can, because you see...
the benchmarks were all at 10 to the 12.
Yes, you see they go very, very up. And then you see if you go to large, so here's R. So even for the smallest R that we have in our table, we get 10 to the 12, 10 to the 13. Of course, you could say, well, if I go to even smaller R, but then the problem is at some point the formula that we used to calculate this is not valid anymore because the formula that is used to calculate these CMP perturbations implicitly assumes that, well, not implicitly, it does assume, the formalism assumes, it is a technical detail, that this gamma coefficient is proportional to t to the 3. If you go to the this effective gamma coefficient, it has a prefactor that's proportional to t to the 3, but it also has this, all this stuff in the denominator. And if you, well, if this stuff becomes too important, then the deviation of the total behavior from t to the 3 proportionality becomes too large to trust the calculation of the CMP perturbation. So when you look at this here, you can see that, the range of values here is kind of limited by the observational constraints and by the reliability of our, prediction. But
so you need large T also because in that denominator there was a term f squared or t squared, right? So if T gets small, the corrections get larger to that. So in that formula which you just showed. That effective rate.
Yes, so well, there's a t to the 3 hidden in there, right?
Oh, true. That's right.
There's a t squared there, so
so it's still going proportional to t.
Yes, so it's still, this thing goes with t, but if I make t smaller, this actually overall becomes smaller, but it's all coupled because h, so to say the stationary t and a, I mean, everything is sort of coupled with everything in this equation, right? But you need large T. It's sort of something that happens near the gut scale. We have neither found a small field realization nor a low reheating temperature realization of this. Okay, this is very high energy physics. But of course, you can turn this in a positive way and say, if we observe this, we probe physics at very high scales. You can always twin everything around and make it sound nice.
So one last question from me. You had a statement in there that reheating is fast. Doesn't that just reflect the fact that you have a lambda phi to the 4th potential? Because oscillations of a scalar field around the minimum of a lambda phi to the 4th potential have an equation of state parameter of 1/3. So basically, you instantly switch from slow roll to radiation domination.
Yes.
Does it just reflect that? Or is there something more to
at
it?
0th order, yes. But we also checked that the period of what you call fast roll is not, we estimated it not to be so long. But you're right.
It's fast, right?
Yeah. No, but I mean, okay, you could argue that there is a period, okay, the statement that you made about the redshifting of phi to the 4 being like radiation is only true when you average over oscillations. So
if you have strong damping,
in
then
principle,
of course
there could be a period between the moment when the universe inflates and before you cross the minimum for the first time and start doing something where I can oscillate over. There could be an excursion in field space where I'm sort of rolling too fast to apply the slow roll approximation, so it's not inflation anymore, but I haven't yet reached the minimum, and I haven't started the phase where I'm allowed to oscillate, to average over several oscillations. And I really have to track in real time the field going down that mountain. And there could be different equation of state that you have to dynamically build. Our estimate was that this period is not very long, so therefore we can assume basically instantaneous transition to radiation domination.
All right, let's thank Marco again.